Okay, let's continue on. We were talking about aquaporin. So if you are able to insert a channel into the membrane of the collecting duct, then you can move water more freely. So let me show you how that happens. This is a little more complicated here, but start out by looking here if we have the collecting duct, okay? And this is a cross section of it, and right next to it is those peritubular capillaries or vasa recta, either one. The capillaries are right next door. So we're going to see sort of yellow, blue, it's pink in the other, white, and then red. That's what we're seeing here. The yellow, the blue, here they made it pink, and then the red. So let's see how that works, inserting these aquaporins. So the first thing on step one is vasopressin, ADH, binds to the membrane receptor. So here it is traveling in the blood, right? In this region of the blood. So it's traveling along, and then what's going to happen is it's crossing this membrane, and it binds to the receptor that's on the collecting duct, the external wall, essentially, of the collecting duct. So that receptor activates a set of enzymes and this second messenger system, and then what happens is that it triggers a set of reactions, and that reaction makes it so that these storage vesicles, which are aquaporins that are sitting, do you notice, in the middle of that cell, they're not in the membrane, but because of this ADH binding to this receptor, it's going to cause a change in this cell, and that change makes for that aquaporin to migrate and insert itself into this region, the lumen side of the cells of the collecting duct. So exocytosis means it's just going to sit there, and now water, then these are able to transport water. So in step 3 here, the cell inserts the aquaporin water pores into the apical membrane. This is the apical membrane. And water is absorbed by osmosis. So now if we've inserted that in there, now water can travel in. So what used to be in the lumen of the collecting duct and was going to just exit the body as urine is now going to be saved. I'm going to save it because I've inserted that aquaporin. I'm going to bring it back into the cell, but it's not going to stop there. It's going to continue on here, and it's going to be absorbed by osmosis back into the blood. Because think of the blood as a stickier, viscous, full of solute substance, and this is watery. So this water is going to go towards the higher solute. So it's absorbed by osmosis into the blood, and I've just rescued that water that I didn't want to lose. And all that because of the hormone vasopressin that was released. So I'm just saying that aquaporins are really brilliant. Who knew that they existed? I mean, it's recent enough that we didn't know that that happened, and that we could insert these channels and allow this water to cross a membrane that ordinarily it couldn't have crossed. So that's everything about ADH, antidiuretic hormone. Now, how does aldosterone work, and what does it do? Well, it's doing something similar. It's saving water. Remember, terrestrial organisms, they need to save water. But it's doing it in a very different way. It increases the active transport of sodium. Where? Out of the distal tubules and collecting ducts. So what it does is it's going to save salt, save sodium. And if you save sodium, what's the outcome of that? Water is going to follow. Okay, so the mechanism is very different. This is released not in response to an osmolarity or too many Fritos, but it's released in response to low blood pressure. So when low blood pressure is too low, you want to be able to save more water so that you can bring that pressure back up, not lose more water. So that's the trigger, low blood pressure. So let's look at my drawing here. Aldosterone removes sodium from the collecting tubule. Okay, so I've drawn my little collecting tubule and sodium. I've taken the sodium back. It resulted from low blood pressure. And then what happens? That sodium is going to migrate back into the blood again. And if it's migrating back into the blood, it's going to bring with it more water. And yeah, so this is, the mechanism is the same. I'm going to reabsorb water that's following the salt and limiting the amount of water that ends up in the urine. Okay, most reabsorption of sodium and water is very early. It's in the proximal tubule. About 70% of that filtrate volume is returned already right away in the proximal tubule. And about 15% is reabsorbed in the loop of Henle. So, aldosterone is the one that's going to do the fine-tuning of sodium. And a lot of that sodium is already reabsorbed before the filtrate even enters the distal tubule. So this is the last chance to regulate that because most of it's already been reabsorbed. And along with it, it'll bring water. So both ADH and aldosterone are going to be able to retain water in the organism, which is a good thing. Don't think of it as a bad thing. It's a good thing because the individual fails to dehydrate. Okay, I wanted to insert a pathology here, given that a lot of you are going to be working with things like this, is finding kidney stones. So stones or renal calculi are these masses made of crystals. They could be crystals of lots of different ions, and they're usually originating in the kidney itself. And from the kidney itself, it's going to have to travel down the ureter and down into the bladder. So lots of that passage there is going to be painful as it travels, as it shows in this poor lady here who's feeling the pain. This is a CT scan, and it's showing a tiny little stone there in the kidney. But really, most of that pain, because they are very painful, it's always this pain is compared to having a baby, might not occur until the stone starts to move down the ureter. So it's got enough space in the renal pelvis, but then when it gets into the ureter, it could start scraping down the ureter. And these stones are not smooth on the outside. Often they are gnarly. They are full of little spiky areas, and that, as it travels down the ureter, can be very painful. It's called renal colic. So here's, for example, a stone that in the pelvis was quite easy. But now when it's coming down here, it could be painful. And it could lodge right where there's a crossing over the ureter. When the ureter is coming over the iliac blood vessels. Let me show you that. So this is the iliac blood vessels. And right when it's crossing here, and there's some pressure of one against the other, and that region there could be painful. Or the stone lodged at the entrance of the ureter coming into the bladder. That's a slight narrowing there that could cause a lot of pain also. So lots of different places to look for these stones when this poor patient is suffering with abdominal pain. Let's see if there's anything else that I want to show you on this slide. I don't think so. And that is the last slide. I want to congratulate you. You've made it through all these lectures in the summer review class. I think you've learned a lot. I really hope you have. And I hope you remember a lot of this by the time you are in your careers, which are a lot of you in rad tech. So that's super exciting. And I wish you so much luck. Take care. Bye.